All right, here we are in video number 3 on acids and bases. We have set up this rice table for our weak acid. We've done a simplifying calculation so that we don't have to do a quadratic. And we have said that the 5% rule is the criteria we need. And now we want to check the validity and make sure that we have that our simplifying assumption is valid. So part J says calculate the percent ionization in this 0.020 molar solution. So we can check our percent ionization and see that the amount we had ionized, which was what we got from our Ka computation up above, was 2.4 times 10 to the minus 5th divided by our original acid concentration, then times 100 to convert it to a percent. And we see that this is in fact considerably less than 5%, so our assumption is a good one. And we can really see that because our Ka value is very small, and we would not expect that this would be a very highly ionized acid. All right, now we want to compare this pH of a 0.020 molar solution of nicotinic acid and the 0.020 molar hypochlorous acid. So we're looking at a comparison of the previous 2 problems we've worked. Which of these is a stronger acid based on pH? Well, the nicotinic acid was 3.26, the hypochlorous was 4.62, and the lower the pH, the stronger the acid. Not a surprise, since we knew that going in because the K value for nicotinic is so much larger than the K value for hypochlorous. So what that means is the larger the Ka value is, the stronger the acid, and the one that has the stronger the acid is the lower the pH. All right, the value of Ka for acetic acid is equal to 1.8 times 10 to the minus 5th. Now we want to compute H plus, the pH, and the percent ionization for the following 3 different dilutions of acetic acid. When we do this, this is relatively straightforward. We can get the H plus concentration by doing an equilibrium calculation. From that we can get the pH, and then from that we can take our H plus concentration and divide that by the concentration of our acid, and we get our percent ionization. So when we do that for all 3 of these acids, we get an interesting result, which seems to say that the more we dilute this acid, the greater it's ionized. And on the surface that may not make sense, but it does if we look at Le Chat's principle, because the more we dilute this the more we dilute the solution, the lower the concentration goes. And so to recover that, to respond to that stress on the system has to move to relieve the stress, which would be to raise the concentration of the things that are dissolved, which means to shift to the right. So when it shifts to the right, our percent ionization increases. All right, a monoprotic acid has only one ionizable hydrogen atom. Acids such as oxalic or phosphoric have more than one, and these are called polyprotic acids. You can have diprotic, triprotic, and there's even one tetraprotic acid that we could talk about. All right, so here are our 2 dissociations. Now you can see that Ka1 is not very small. It's in fact 0.017. It's pretty reasonably large, but Ka2 is 1,000,000 times less than that. So this means it's going to have a hard time getting rid of that second hydrogen, but a pretty easy time getting rid of the first one. Okay? So as we've just seen, Ka1 is usually much larger than Ka2. Therefore, when calculating the pH of a polyprotic acid, we can essentially treat this as if this is monoprotic. There's only going to be a very small acid contribution from the second and especially the third ionization. And for our purposes in AP chemistry, those are insignificant, assuming that the Ks are far enough apart, and this allows us to focus just on the first ionization. Okay? Now we're going to do some math problems. Sulfurous acid has the formula H2SO3. The Ka values for sulfurous acid, we can get that in the problem above, so we want to calculate the pH of this sulfurous acid. Now we can write our equilibrium expression. Hopefully we would like to be able to assume that x is negligible so we don't have to do a quadratic, but in fact we see that K is fairly large, and so our assumption that it's insignificant compared to 0.01, that's probably not going to work, and we're going to be stuck having to do a quadratic. So if we are stuck doing a quadratic, when I solved this, I got 0.034, and therefore pH is 1.47. You should pause the video, and you should do this yourself. Part 2, calculate the concentration of the sulfite ion in a 0.1 molar solution of sulfurous acid. So now Ka is significantly smaller, and we can write our Ka. We know the concentration of H+, but what we don't know is our sulfite ion concentration, but we know our Ka too is pretty darn small. And it seems like we could get away with making this assumption. So let's try that and see if it works. When we solved this, we knew that H plus was already 0.034 from the previous problem up above. So we can plug that in. And when we solve this problem, we end up getting x is 6.4 times 10 to the minus 8th, which is in fact the value of the K. All right, as you can see, this isn't the second as ionization step only occurs to a very, very much smaller extent. All right, section 7. Let's talk about bases. We can write a generic weak base as B, so let's write our ionization. B plus water reacts to form Hb plus OH minus. And when we write our K expression, we get Hb plus times OH minus over B, leaving out, of course, the water. And we're asked to determine which of these two substances is the stronger base. And a larger Kb equals a stronger base, so our methylamine is the choice for the stronger base. There are two categories of weak bases. There are neutral molecules with an atom that has a lone pair of electrons that can accept this H+, and then there are anions that represent the conjugate base of a weak acid. All right, part D, amines. They are organic compounds that contain a nitrogen atom with a lone pair of electrons, and examples are these three Lewis structures below. We want to circle the one that represents the strongest base, so of course we have to look at our value of Kb. And when we do, it's not a surprise that methylamine is the strongest base among the three. The hypochlorite ion is one example of a basic ion because that's the conjugate base of hypochlorous acid. And the formula of this ion is OCl-, and its Kb value is 3.3 times 10 to the minus 7th. Another example would be the cyanide ion, which is derived from hydrocyanic acid. All right, now you're given a concentration of a weak base and the pH, and it's possible to calculate the value of Kb. So if we have a pH of 11.33, it's easy for us to get the pOH because we subtract it from 14 and get 2.67. What's the concentration of the hydroxide? Well, we take 10 raised to the negative 2.67, and we get 2.1 times 10 to the minus 3. What's the concentration of ammonium in this solution? Because the stoichiometric coefficients are all the same, then the ammonium concentration is the same as the hydroxide ion concentration. And we're going to plug these in to the value for the Kb expression. There's our reaction equation. There's our Kb expression. We plug in our numbers and we get 1.8 times 10 to the minus fifth, which happens to be the same number as the Ka for acetic acid, but this is strictly a coincidence. These two reactions have nothing to do with each other. All right, if you're given the concentration of a weak base in the Kb, can you calculate the pH? Of course, the answer is yes. So we've got ammonia with a concentration of 0.05 molar, and we're asked to calculate OH minus, pH, and percent ionization. We write our reaction and make sure it's balanced. We write our equilibrium expression, of course, leaving out the water. We plug in our values. We set it equal to our Kb. We make a simplifying assumption that X is insignificant compared to 0.050, which feels right because Kb is pretty small. When we do, we get X is 9.5 times 10 to the minus fourth. So pH therefore becomes 10.98. From 9.5 times 10 to the minus fourth, we would get POH, and then subtract that from 14 to get our pH of 10.98. Now, percent ionization. We take our OH minus concentration, which is 9.5 times 10 to the minus fourth, divided by our initial base concentration, multiply by 100, and we get, we get 1.9%, which shows us that our assumption of less than 5% is a valid assumption. All right, now, part I. We have a 1 liter solution of sodium hypochlorite, and we're asked to calculate 5 things from this, which seems like a lot, but it's straightforward. All right, we write our reaction. We have the hypochlorite ion plus water forms HOCl plus OH minus. All right, our POH is 14 minus our pH of 4.5, our pH of 9.5, giving 4.5 for POH, which allows us to compute our OH minus concentration, which allows us to compute our HOCl concentration. So now we have the first 3 things. To find OCl, we're going to need a rice box. We set up our rice box with our equation that we just did. We set up our initial concentrations. We know the change in these concentrations we get from our pH and POH calculations. So now we have our final equilibrium, and we can plug that into our Kb. Because Kb is pretty small, we can be pretty comfortable that our assumption, our 5% assumption, is going to work. When we plug that in, we solve for X, we get 0.0331. And when we multiply that times our molar mass of 74.44, we see that we have 0.23 grams of sodium hypochlorite. Kind of a long question. Wouldn't surprise me if you saw something like that on an exam. All right, we want to look at section 8, the relationship between Ka and Kb. And we're asked to put in the missing information. All right, so when we look at this, we can see that Ka, of course, this is old hat right now, Ha times A minus over H plus times A minus over Ha. And when we have a conjugate base, we can say Kb is Ha times OH minus over A minus. When I add these two reactions together, you can see that the HAs cancel and the A minuses cancel, leaving me with just a water reaction. And when I add those two together, I have to multiply their Ks, and when I do, several things cancel, leaving me with just my Kw reaction. So we want to write the relationship between Ka, Kb, and Kw. We get this one, which we've seen before. And again, for the P function, 14 is equal to pKa plus Kb. And so now we can easily compute our pKa's for acetic acid and hypochlorous acid. We'll stop there. This is the end of part 3, and we'll pick up in a minute.